Okay, guys, so before we do what we before we do this justification here, if you'd look up front. All right. So yesterday we spent all this time, like I showed you, we learned how to multiply vectors. We know how to add vectors by going tip to tail. Now, and then we learned how to multiply. We're doing all of that just so that we can explain this, prove that this is true. Now, the other little bit of information is something else that you need to know from geometry. Okay, so if you look up here, so if I had, you don't need to draw this, just look up here. All right, if I took that triangle and I doubled all the sides, okay, so I made this side is now going to be 6. 1, 2, 3, 4, 5, 6. Okay, and this side is now going to be 4, 4, and we got that. All right, now these two triangles, if I just call this one, let's see, ABC, and call this DF, DEF. Okay. All right. In geometry, we said that these two triangles were similar, and this was the symbol for it. And it's because this length right here, this the side that's opposite B, we'd call little b. And what I did was I made this side twice that. Okay, the side over here I called little, this would be little c. I made it twice as long. Okay, this side A, this one would be twice as long. So everything got doubled. All right, if you do the ratio of the big to the small, okay, 2A over A, and then you did 2B over B, and 2C over C, okay, all of those simplify to the same ratio of 2 over 1. So when that happens, then we say that these triangles are similar. Okay. Now, if triangles are similar, what is true about their angles? So is angle C is angle F twice as big as C? No, they're the same. So we say that the corresponding angles, angle C is the same as angle F, angle B is the same as angle E, and angle A is the same as angle D. Okay, the angles are the same. The side lengths are proportional because we doubled everything. Okay, that's similar triangles. So we need that in what we're doing today. Okay, so now let's go to this. Okay, we want to justify that when you multiply two vectors, the amount that it turns is equal to the sum of the rotation of the two other vectors. Okay, the two other complex numbers, I mean, right? Okay, so to do that, get a pencil here. Okay. Oh, geez. Okay, hold on. All right, so yesterday we learned how to multiply two vectors. So on your paper right here, okay, let's write let W equal A plus BI. It's some vector or some complex number. And for the sake of argument, we're going to put it like, we'll put W right here. At about, put it at like 3, 1. Okay, and then we're going to use one color and connect that point there. We're going to label that W. That length is W, okay? That would be like the modulus of W is that length. Okay, and then we're going to take that and we're going to multiply it by some another complex number Z. And since so that we all draw the same one, let's put Z at 2, 2. And just kind of faintly, that's Z. We're going to be coloring that a different color here in a few minutes. Don't label anything on this. We're going to be labeling it here in a minute. But that's where Z is right now. Z's right here. Okay. All right. Now here's what we're trying to prove. We're trying to show that this isn't what we're trying to prove. This is how we're going to prove it. If I took W times Z, those two complex numbers, and multiplied them, right? So what we did yesterday was I'm going to substitute ABI for W, and I'm just going to leave Z, the complex number Z, as Z. Okay, this is what we were doing on the whiteboards yesterday. Okay, then we said, well, how do you multiply those two? So if I distribute this, that's going to be equal to A times Z plus BI times Z. And then what we did was we drew each one of these and then we added them tip to tail. That's how we multiplied. That's how we turned a multiplication problem into an addition problem. All right, so what I have to do now is I got to draw this, AZ. So A times Z. Now what's A and Z in this case, or A and B? Well, if you look over here, let's use another color. This length right here, okay, the one that I'm kind of doing in blue, that's A. That's how long A is right here. And then this is in another color, this is the kind of length of B. So I made that one green. All right. Any questions on what those numbers mean, right? How I'm getting those numbers. This is A plus BI. Good to go? All right, now, here's what we got to draw AZ. Well, how many more Z, how are we going to draw that? How are we going to dilate Z? By what factor right now? By 3. So I'm going to make Z 3 times longer. Okay. And I'm going to use the same color that I used on A. So this is 1Z, another Z, 3Z. So I'm going to label that blue line. I'm not going to write 3Z. I'm going to write AZ. That's how long it is. Okay, so we drew this. This, in my case, this was blue. Okay, now we got to draw this line, BIZ. So we're going to go back to our original Z. What does the I do to it? Rotates it 90 degrees, and then the B is going to make it longer or shorter. Well, B is equal to what here? 1. So it's not going to make it any longer or shorter. This is just going to rotate Z 90 degrees. Okay, so if I'm going to rotate Z 90 degrees, all right, it's going to go in this northeastern direction, and it's going to be perpendicular to that blue line. Okay, and I'm going to use the same color that I used for B. So this is going to be BZ. Okay, so I'm going to label this BI times Z. So this one's a multiple of, it's Z multiplied by whatever that length is. And the blue one is Z multiplied by whatever A was. Okay, now so on my drawing, this is green. Now I want to add this line and this line. So the way we did that was we took this and we slid it to the end of this and redrew it. Okay, so that's going to come right up here, and I'm going to redraw it right here. And that's the length BZ. I should have just wrote this was BZ, not BIZ, but that's okay. All right. And now draw your product. That's this line. So make this the same color as W. And we can label this now W times Z. That's the product. So that's what we spent all yesterday learning how to do, just so that we could draw this picture and it would hopefully make a little bit of sense. Okay. Now, what's true about these? Just so that we have a way of talking about it, let's label the corners of these two triangles here. So I'm going to label the origin O. I'm going to call this triangle P, Q, and O, just so that we can talk about it and you know what I'm referring to. And we're going to call this triangle R, S, O. Okay, now what's true about those two triangles? Look at, are they proportional? So if I take this length, OQ, and I compare it to OS. Okay, so if I take OQ and I compare it to OS, okay, OQ, or let me do it the other way. Let me put the longer one on the top and the smaller one on the bottom. So I'm going to go OS, OQ. Okay, now OS is this length and OQ is this length. So if you simplified that, that ratio simplifies to Z. Okay, now compare the ratio of Q to P and S to R. That's the two green sides. That's why we color coded them. Okay, oops, I got to put the bigger one on top just so that we're consistent. So this is SR and this is going to be QP. Okay, so SR is B times Z, QP is B, and that also simplifies to Z. So right now we say that these two sides are proportional because their ratio is the same. They're both Z. And now if you compare WZ, which was OR, you compare that to OP, and that's WZ divided by W, and that equals Z. So it's just like the triangle that I showed you before. It's like I doubled every side. In this case, what did we do to the sides? So we're getting the same proportion. You see the ratio here is the same. When I simplify that, it's Z over 1, Z over 1, Z over 1. So we can say the sides are proportional. That says the sides are in proportion. And if the sides are in proportion, then you can say that triangle ORS, that's the big triangle, is similar to triangle OPQ. That's the small triangle. So we did all of this just to show that these two triangles are similar. Okay. All right. Now, what we're trying to do is prove this stuff about the arguments. Okay. Okay. What angle up there would be the argument of W? What's the angle that's the rotation of W? Yes. Yep. So POQ, this is the argument for W. Okay, so I'm just going to do this. I'm going to shade this guy in just a little bit like that. Okay, draw a little line to it and say that's the argument of W. Okay, now what angle is that equal to in the big triangle? Use these big letters. Okay, so you use the point that where the vertex of the angle is, that goes in the middle. ROS. So I'm going to color this in. Those two angles are the same size. That's the same as the argument of W. And if someone said, well, why? It's because the triangles are similar. So if the triangles are similar, these two angles have to be the same size. All right. All right. Now, where's the argument for Z? What angle is the argument of Z? Use 3 letters. Q. No, it's got, you're looking for the angle from this blue line to that blue line. Yeah. It's S, O, Q. So this is the argument for, that's the argument for Z. So this guy, this was the argument for W. I'm going to, let's see, make this red. Okay. Now, what's the argument for WZ? ROQ, yep. Okay, now how can we use that to get the statement that we're looking for, that the argument of WZ is equal to those two arguments added together? See, if you look at the argument of WZ, it's made up of this angle right here, okay? And it's, well, actually it's made up of angle, the argument of the blue one, which is the argument of Z. What's this little angle in here? Yep. You just proved it. You just proved this. That's why that works. Okay. So just by now you can geometrically see that when you, this argument right here, when we look at it, is equal to the argument of W, which is this little red slice here, plus the blue angle, that's the argument of Z. And then you write Q, E, D. QED means it has been shown. It's the Latin, I have to look up what the Latin saying is, but it translates into it has been shown. So we just established that this angle right here, this argument, is equal to this argument plus this argument. And that's a proof. Okay, now you don't do too many of those in high school, but that's what's called a proof right there. You're showing why something is always true. Okay. The other proof that we did was, let's see, when we did the whatchamacallit, the magnitudes. Okay, that was this, right? Let's see. Right there. Okay, that right there, that was the justification for this rule. See, so there was two things that we have now justified, because that's the title of these notes. It says the justification of the geometric effect of complex multiplication. Okay, so here's the justification for this rule. Okay, and the justification for the argument part of it is what we just did. That's the justification for the argument part of that rule. So you've proven both things to always be true. Okay. So, there are times where, in most math, you just learn, okay, here's the rule, here's the rule. In this case, we established the two rules, and then we proved why they were always true. Okay, which is the way that mathematics works. Someone sees a pattern, and they're like, hey, I think this is always true. Well, then a colleague's going to say, well, prove it. Well, here's the proof. Okay. All right, so let's go back to our packet now. Okay, this is going to go with your packet. Just staple it to it. Just staple it to lesson 15. For me to plot 3 pi over 4. So here's pi over 4. So that's 45 degrees. All right, so I'm going to plot 45 degrees, okay? And that length is going to be 3. Okay, so let's see. Length is 3. So whatever this length is right here, the line that you draw is the same length as that, but it's going at a 45-degree angle. This side and that length are the same. They're both 3. So I'm going to say W is something like that. Okay, so there's W. Okay, and now Z is 2/3 negative pi over 2. Well, negative pi over 2 is clockwise. Okay, so that one is going to be 2/3. It's not quite to -1. So Z might be located some spot like that. Okay, any questions on what I did there? All right, now you can figure out what WZ is, knowing what we know about our two properties. Okay, so we know that the modulus of WZ is going to equal the product of the modulus of W and the modulus of Z. Okay, so that's going to be 3 times 2/3, which is 6/3, which is 2. Now we need to know what's the argument for W. Well, we know that the argument, what we just proved was the argument of WZ is equal to the individual arguments added up. The argument of W plus the argument of Z. Okay, so that's pi/4 plus negative pi/2. Okay, so now I'm going to add those two up. So get a common denominator. That would be 4. So this is going to be pi plus negative 2 pi/4. So that's negative pi/4. So this would be 45 degrees clockwise because it's negative. Okay, so now you can draw WZ. Okay, WZ is going to go this direction, 45 degrees or negative pi/4, and it's going to have a length of 2. So it's going to look something like this. That's going to be W times Z. Okay, this right here, this is, that's the rotation right there. That's negative pi/4. So we're using the shortcut now to get these, to get the argument and to get the argument and the modulus. Okay, questions? All right, let's try the next one here. Okay, W is 2 and its argument is pi. So a rotation of pi is that. Okay, so I'm going to put W. W is going to end up right here. Okay, Z has a length of 1 and it's pi/4, so that's 45 degrees again. So it's going to look something like that. Okay, now let's multiply the two. Okay, so to get this product, we know that's going to be the product of W and the product of Z, which is 2 times 1, which is 2. So that's how long our line's going to be. And now to get its angle, you add the two angles. So the argument of W plus the argument of Z. So that's pi plus pi/4. Okay, get a common denominator. I had to make this a 4. So I got to multiply the top by 4, and I get 5 pi/4. 4. Okay, well, how far is 5 pi over 4? Okay, so 5 pi over 4, guys, would start here, and it's going to go all the way to there. There's 5 pi over 4. And its length is equal to 2. Right? So whatever this length is right here, I'm drawing it to be the same length as that. I'm just kind of eyeballing it right now. And that would be W times Z. And this length is 2. And this angle is 5 pi over 4. Okay, can I move that? Okay, so I guess we'll do this Monday.